plate or whatever, the sandpaper, I pulled those off, called all the ash, anything that actually had mass off, and I looked at that total mass afterwards, that difference would be the amount of energy that got converted into flame, in essence. And flame and other radiation.
I'm sorry, what's C in our rest equation?
What's that?
C. It's this,
See, that's speed of light,
okay.
about 300 million meters a second, just shy.
So if we're including combustion under rest, that means we have chemical properties in both potential and rest, right? Because combustion is a,
When you have a chemical bond, it's potential energy. When you break that bond and energy is released, some of that potential energy gets converted into rest. That energy released is coming from the rest energy.
okay.
All right,
Energy.
now in terms of symbols, that's probably potentially the last time I talk about rest energy. So I'm gonna erase it, because that's for another time. These two energies together make up what is known as mechanical energy. And so the total energy, you generally, at this point in the course, when you're saying total energy, it's understood mechanical energy. Sometimes textbooks will throw in, hey, what's the mechanical energy? All they're asking for is just the kinetic plus potential. And so E is equal to K plus, and as you would expect, the symbol for potential energy is a capital U.
Huh?
Because you have potential.
Oh, well,
Aw, that's a good way to remember it.
I definitely won't remember it.
You are potential.
You have mass and you take up space, so you matter.
And I think this one is from the German, but not 100% sure on that one. Why? You. Some textbooks will use a capital V because why be consistent?
Yeah. You know, it's funny, we use a lot of Greek alphabet letters for like math, but getting into this, like thinking about using Greek letters for other things, it's kind of like throwing me off. Not in a sense of like, I don't understand, but in a sense of like, why would we keep using Greek words in like different languages for stuff? Well, I guess international, understanding of math and physics and stuff like that, but from the same alphabet or from the same language.
I was flashing back to my first year of teaching. I set up a triangle and I had alpha, beta, gamma. And a student said, that's not right. I said, what? It's not alpha, beta, gamma. It's capital A, capital B, capital C.
Yeah, I mean, didn't most of the science terms that were named after like Latin and stuff were named in a period of time when lots of people were, like when there was like a revivalist period for like Greek and Latin culture.
Hmm.
So like people looking back at old mathematicians and like the rejuvenation of the sciences.
Gotcha.
And so people looked back at Latin and just chose that as like the scientific language.
Yeah.
So a lot of this stuff was named like the 1800s.
And earlier, Newton wrote his major work in Latin.
Isn't that during the Renaissance? Or no, that's...
Newton was 1600s, late 1600s. I'm pretty sure he was after the restoration of the crown. Anyway,
Yeah.
I don't think people are naming new things with Latin terms for the most part, are they?
oh, still doing it?
Yeah, most of that's already happened.
That's my understanding. I mean, physics at this point, English is a rather international language on that one, so probably a lot of things on that.
Yeah.
Now, let's connect various things here. I have work, total work, is changing kinetic energy. That was the first thing we derived. I'm not gonna offer a derivation of it, but if I have non-conservative work, again, it's called non-conservative because it's taking energy away from one object and giving it to another. So non-conservative work causes change in energy. Now I'm gonna combine the two for the third version of this. So work total, well, there's only two types, there's conservative and non-conservative. That's equal to the change in, oops, there should be NC there. That's equal to the change in kinetic. Just work total is, it's all the conservative work plus the non-conservative work. Non-conservative work is change in energy. So this should be plus delta E is equal to delta K. Energy, well, there's kinetic and potential. We're not worrying about rest. So that's work conservative plus change in potential plus change in kinetic is equal to change in kinetic. Kinetics cancel out. Bringing delta U over, we get work conservative is equal to the negative change in potential energy. These are the work energy relationships.
Are they gonna be like cake formulas where we'll need to just know them for stuff we do generally?
Not quite as extensive. This is the starting point for a number of things that we're gonna do. At some point, you'll skip past the introductory stuff where we're actually using this, but this will be our justification for some shortcuts we'll take later.
Okay.
So if I have an object here that is going up in the air, we have ground, and it starts out at some initial height, and it goes to some final height. It's already, so an object's been thrown into the air, how it got moving, I don't care, it's moving, going up. If we do a force diagram of this, what are all the forces acting on that mass?
Force of gravity.
Weight down
Wait.
and up on the ground.
Okay, only care about the ball right now, but yes, you're right. What else?
What is the HF and the H?
That's the initial height and the final height.
Okay. There's definitely another force.
Why?
Why else would it be?
Or-
Why else would the height be going up?
Well, it has an initial velocity, but that doesn't necessarily institute a force.
Are we just like throwing out air resistance, all that?
Absolutely.
There
Okay.
should be nothing else.
So no air resistance. Why it got moving to begin with, I don't know. That's part of a different problem.
Okay.
It's already moving when we come back from commercial, it's already moving.
Okay.
Also, I'm backtracking. You circled these and said there were work something relationships.
The work energy relationships.
Okay, and what is, that's supposed to be a negative, right? Like
Yes,
negative-
that is a negative.
Okay, negative change in potential.
Yes.
Work energy.
Weight, is it a conservative or non-conservative force?
Conservative.
So we're gonna use that third equation. So work conservative is equal to the negative change in potential energy. Work is force times displacement. So I have my weight vector, dot product with my displacement, is equal to negative of U final minus U initial. Now weight, dot product with displacement, weight is acting down, displacement's acting up, they're in opposite directions. The angle between them is 180 degrees. Cosine of 180 degrees is,
2, or no, 1. No, give me a second. -1.
yes, -1. So this dot product here is just gonna be the negative of weight times displacement, which is negative U final plus U initial. And so this becomes negative mg H final minus H initial, or negative mg H final plus mg H initial. and that's equal to negative U final plus U initial. So starting out with basically, we started with the definition of what work is, and minimal hand waving, we got to this formula right here. Now applying this specifically to this case, we have this relationship here. So now the question is, what is an equation for U that would make this work? Or what formula can we, if I needed to come up with a formula for U so that this is true, what is a formula that would work?
What were some of the ones you were writing? It was like one for, like gravity and.
Yeah.
O
And?
equals 1?
No, if U is equal to 1, then we'd have 0 on this side.
Right. Okay, never mind.
Well, we have to factor out F and, well, we're trying to find the total U, right?
I'm just trying to come up with a formula for U so that this is a true statement.
U is equal to MGH.
So does that work? If U is equal to MGH, then U final, this would become negative MGH final plus MGH initial. That's what we have over there. So U is equal to MGH works. What's another equation that would also work? There are an infinite number of them, so
U is equal to W times displacement, so weight times displacement.
no, that's how we got, that was related to delta U.
Okay.
I'm looking for a formula for U so that this works.
Oh,
Weight times height in the same vein?
That's the same thing.
Negative MGH?
If you did negative MGH, then we'd have negative MGH final plus negative MGH initial, which becomes MGH final minus MGH initial, and that's not the same thing we have over here. So that would not work.
It's not the same thing even with the commutative property?
Say again?
Even with the commutative property, it's not.
No, it doesn't.
Okay.
No commutative property of subtraction.
Oh. Okay.
Or at least if it does exist, I've never seen it.
this is a trick question, that's the only,
No, there's a whole bunch more. It's not complicated more, it's just a bunch more.
Can you give us an example of one? Because
I actually gave a hint earlier when I was writing down the formulas.
1/2 K times
When I wrote down MGH, I then tacked on something else. Yes, if I made this MGH plus 1,
Oh,
then this becomes negative MGH plus 1 plus MGH initial plus 1. I get negative MGH final minus 1 plus MGH initial plus 1. The ones cancel out. Anytime any constant I tack on here is going to cancel out. So that's why I wrote the formula as MGH plus a constant. So the actual value, since any constant can work here, the actual value of potential energy is not critical. What really matters is the change in potential energy. Because if I have conservative work going on here, conservative work causes energy to flow. If it's conservative work, that energy is flowing from potential to kinetic or kinetic to potential. If it's non-conservative work, I'm taking that energy and I'm transferring it to a different object. Or I'm taking it from another object and transferring it to them. When I push this table, right now there's no energy in it, I'm about to do non-conservative work, it's a normal force. As I push it on the table, I gave it energy. It started out rest and then suddenly had kinetic energy. That energy had to come from somewhere. I burned off some calories doing that. And that's my exercise for the day. That is a really bad role model. When you are in your late 50s, that better not be the only thing you do for exercise.
Pushing a table.
That's right.
tricycle.
But it was an incredible example of pushing a table.
Of course.
So, on that note, see you Friday. I guess there's quizzes on Friday?
Yeah.
Earthquake.